We've seen that Babbage and Lovelace's mechanical devices could compute, that cellular automata can compute, that even Wang tiles that are trying to fit together and cover the plane can compute. What about dynamical systems? Here is a diagram of a chaotic dynamical system called the Baker's map. What it does is it takes points that lie in the unit square, so x and y both range from 0 to 1. It stretches the square, then cuts off the top half and puts it down here on the right. So it stretches, cuts, puts this down on the right, stretches, cuts, put this down on the right, each time you run it. So as a result, the x-coordinate at every step is getting squeezed, the y-coordinate at every step is getting stretched, but if it's bigger than 1, it gets cut off and put back down. So we can write this mathematically by saying that at each step, y becomes 2y mod 1, where by mod 1 I mean if it's bigger than the integer 1, subtract 1, so that you again get a real number between 0 and 1. X goes from x to x over 2 if you're in the bottom half of the square, because then you just get smushed over here, and it goes to x over 2 plus a half because if you're in the top half of the square, because then you get stretched over here and then put down there on the right side. So, why is this an interesting dynamical system? Well, for one thing, it's chaotic. If you have two initial conditions which are quite close to each other, then unless their y-coordinates are exactly the same, each time we stretch in the y direction, the difference in along the y-axis will get twice as big, twice as big, twice as big, until eventually one is in the top half and one is in the bottom half, and after that they're in essentially unrelated places. So these small differences in initial conditions will get exponentially amplified over time, which is one definition of chaos in dynamical systems. Now, let's do something kind of cute to the binary digit sequences of the x and y axes, the x and y coordinates. So I'm going to take that decimal point or binary point and write the x coordinate over here, the halves digit, the quarters digit, the eighths digit, and so on. So I'm going to take that real number and write it to the right of the decimal point as I normally would, but in base 2 instead of base 10. I'm going to take the y coordinate and do the same thing backwards. So it constitutes the left side of my sequence. In fact, I claim this is a particularly simple example of a Turing machine. So one of the things we're doing to x is dividing it by 2. So if you have a number written out in binary and you divide it by 2, it's going to shift all those bits down away from the decimal point, leaving a space up here at the halves digit. But what do we put there? Well, we add a half to x, putting a 1 here, if y was bigger than a half. But y being bigger than a half, well, that is if the halves digit of y is 1. So this entire operation consists of shifting over the decimal point, taking the halves digit of y and moving it into the halves digit of x. So this is a particularly simple Turing machine where the decimal point is the current location of the head, and all it does is move left, transferring bits from the y-coordinate over to the x-coordinate. It doesn't read or write them or modify them in any way. Now let's simulate a Turing machine which does read and write, which has a couple of internal states, and which actually does something to these bits. Well, as you can imagine, we're going to get a more complicated version of this dynamical system like this one. So here at the top we have this rectangle. It's divided into a bunch of squares and rectangles which represent combinations of the tape symbols, which are bits, and the internal state of the Turing machine. If we move left, then those squares and rectangles get stretched this way and squashed that way. If we move to the right, then they get stretched this way and squashed that way. And then to read and write and to change the internal state, we're going to displace some of these rectangles from one place to another. So if you follow this map, if you continue iterating Every time you have a point in that top rectangle, you follow the map and figure out where it should go. Then you do it again and again and again. You're literally carrying out steps of a Turing machine computation, and in particular, a small universal Turing machine. So, and by the way, this kind of thing was in my PhD thesis, so I guess I'm ringing my own bell here, but the point is that this dynamical system, which is not that much more complicated than the classic Baker's map, is doing universal computation. As a result, all of its long-term behavior is undecidable. So even if I describe this map to you with perfect accuracy, telling you exactly where all these rectangles lie and where they end up, and I give you an initial point, x comma y, somewhere in this rectangle, it is undecidable, uncomputable to tell whether, as we iterate the map, it will ever fall into a particular region, because that region could correspond to the halt state. It's undecidable to tell whether that point is periodic, whether it will ever return to where it began. It's undecidable to tell whether it lies on a chaotic trajectory, if indeed it is one of those points where a small perturbation to that initial condition will cause an exponentially growing difference down the road. Since all of these questions correspond to the halting problem, they're all undecidable. And I want to point out, this is worse than the type of unpredictability we usually have in chaotic dynamical systems. Usually what we say, a butterfly flapping its wings and causing a hurricane 6 months later, etc. Usually what we say is that chaotic dynamical systems are hard to predict because we don't know things exactly. And even a small error in the initial condition will get exponentially amplified over time until we really have no idea where in the system's state space it is. This is different. This undecidability holds even if the initial condition is rational with a finite number of binary digits, even if we know it exactly and can write it down with no error whatsoever. So, this is a very strong type of unpredictability that comes from undecidability. I want to end this unit by just pointing out there's a lot of naturally occurring dynamical systems which seem difficult to classify computationally. Here is another chaotic map in 2 dimensions called the standard map. You can see it as all kinds of complicated structure, all sorts of basins and periodic orbits where it can get stuck for long periods of time, slowly escape from them and end up somewhere totally different. It seems hard to predict. It is hard for me to imagine an algorithm which can look forward in time much faster than we could by literally simulating it step by step. I highly doubt that there's any shortcut to predicting the eventual fate of an initial point as we apply this map over and over again. On the other hand, I don't see how to build a computer out of it either. It seems too messy. It doesn't have these clean boundaries like the ones we designed into that map I showed you before, with those rectangles and squares corresponding precisely to some combination of a tape symbol and a Turing machine state, and a transition which corresponds precisely to writing some new symbol and updating the state. So it's possible that the long-term behavior of naturally occurring systems like this is undecidable but not universal. There may be no algorithm to predict what will eventually happen. At the same time, it may not be the case that we can translate the halting problem into a question about this chaotic dynamical system. There may be no way to reduce halting to that long-term question. So many dynamical systems occurring in the real world might be in this messy middle ground where they're too complicated to predict. We just have to simulate them and see what happens. But they're not controlled enough to actually use to build a computer out of and thus prove that their long-term behavior is uncomputable. That would be a funny situation to be in, because there would be no algorithm to predict them, but we would have no way to prove that there is no algorithm to predict them, because it wouldn't correspond to the halting problem.